now leading our plenary session on heterogeneous 3D microsystems, Chief Scientist at TSMC and Professor at Stanford, Dr. Philip Wong.
Good morning. I'm Philip Wong from TSMC and Stanford University. My message today is very simple. The future is system integration. In the past few decades, the semiconductor industry has been extremely successful in integrating discrete components into billion transistor chips. Now, in the coming decades, we must go beyond a single chip on a wafer and focus on integrating chips into systems. Let us start from the application needs. 21st century applications are going to be data-centric. Data analytics, machine learning, and AI applications are going to dominate, from data center to mobile and IoT, from collecting and processing to curating the data to derive information. Many systems will need to learn and adapt on the fly. For this talk, I'm going to focus on technology trends and solutions with these abundant data computing applications in mind, namely data analytics, machine learning, and AI. Here, this graphic shows system throughput per watt on the y-axis and a range of tasks that can be executed on the x-axis. The CPU can execute a variety of tasks and has been the mainstay for computing. The emergence of abundant data computing made the system throughput and system throughput per watt the key performance metrics. These metrics can be improved by more and more specialization from CPU to GPU to TPU and accelerators that are able to execute a narrow set of tasks in a massively parallel fashion. In other words, flexibility has been traded off to maximize system throughput and energy efficiency. With this in mind, let us look at how the performance of these specialized architectures can be improved at the system level by advances of the underlying technology. Data-intensive computing systems, by their very nature, require optimizing memory and memory access along with compute. In order to illustrate attainable performance limits imposed by compute efficiency and memory access on a single graph, we will be employing the roofline plot. Here, we have system throughput in operations per second on the y-axis and operational intensity in operations per byte on the x-axis. Ideally, processor peak throughput and memory bandwidth should improve simultaneously such that the flat and the slanted portions of the roofline can be lifted up in parallel. The processor peak throughput is the product of the number of cores, the core frequency, and the number of operations per cycle. The memory bandwidth is the product of the bus width, the bus frequency, and the data rate. The core frequency and bus frequency are no longer efficient knobs to drive the growth due to limitations by thermal design power and/or power density. The number of operations per cycle and the data rate depend on the tasks at hand, the architectural design, and industry standards, which are transparent to the underlying hardware. From a device technology perspective, the key area for growth for processor peak throughput is the number of cores by introducing even more parallelism. And for the memory bandwidth, the bus width has the most potential to grow because the technology to do so is ready, as I will elaborate on later. These opportunities point to an important observation. We need more transistors, more memory, and more connections between transistors and memory combined in a package to improve system throughput. In the coming slides, I will illustrate these points based on the server and data center GPU trends related to throughput and bandwidth. Starting with the peak throughput, the data suggests that throughput improvement is mostly due to the increase of the number of cores. While clock frequency is an important performance indicator for CPUs, for abundant data applications such as data analytics and AI that uses GPUs and accelerators, throughput is a strong function of the core count with close to one-to-one correlation today, rather than the clock frequency. And because the average transistor count per core has remained roughly the same, the peak throughput is a strong function of the number of transistors on the chip. So it is really important to keep providing more transistors. This is the first point I would like you to keep in mind. Of course, all these logic computation require data from memory. Next, I want to talk about memory bandwidth. The bandwidth is simply the data rate times the bus frequency times the number of I/O or bus width in bytes. The bus frequency, similar to the processor clock frequency, grows at the expense of added power. The power-friendly knob is the I/O count and, more specifically, the bit width per memory channel. The peak bandwidth grows at about 1.56 times on a 2-year cadence. This is slower than the peak throughput growth rate of 1.8 times on a 2-year cadence for logic. Thus, there is a bandwidth deficit, and this would limit the system throughput for a broader set of tasks. To increase bandwidth and bandwidth per watt, the most effective knob is to increase the I/O count. Fortunately, there's a lot of room for the I/O count growth, as we will discuss on the next slide. Vertical interconnect density associated with advanced packaging featured about 3 to 4 orders of magnitude improvement in the last decade alone, using a variety of chip-level and wafer-level technologies. Today, the bond pitch between the top dies and the interposer is about 40 micron. Using SOIC technology, which I will describe later, the bond pitch can be down to about 9 micron. And if we go monolithic, the interlevel vias can be 100 nanometer or below. So there is at least another 4 orders of magnitude to go as far as bandwidth improvement is concerned. In addition to a dramatically increased off-chip interconnection density, another technology knob to address the bandwidth deficit would be putting high memory capacity right on the logic chip. Within the context of the roofline model, a higher on-chip memory bandwidth made possible by a wider bus would result in uplifting of the slanted portion of the roofline, similar to how an SRAM cache would improve the bandwidth. This is illustrated by the cartoon on the right. Putting memory right on top of the logic chip would improve the bandwidth and bandwidth per watt if, let's say, an entire deep neural network model can be fit onto the on-chip memory. Shortcomings of the non-volatile memory, such as high write latency, can be mitigated by the much wider bus width provided by the high connection density between compute and on-chip memory. So far, we have discussed the fundamentals of abundant data computing systems. For the rest of my presentation, I would like to talk about the specific system integration technologies. Bear in mind that when we talk about the technology, the attributes that matter include not only system throughput and power consumption, but also form factor, time to volume production, and cost. Here, I show some examples of various system technology integrations in use today. Starting from an SoC, or system on chip, at node N, one can partition the die into several chiplets. Each chiplet can be of a different technology node. This chip partitioning adds design flexibility and reduces design non-recurring engineering costs. Because some of the designs of more mature nodes can be reused, this may even shorten time to market and reduce cost. There can also be memory chips such as DRAM, SRAM, MRAM, and RRAM added into the mix. These chiplets can be stacked, as shown on the top branch, onto a passive redistribution layer, or RDL, in the form of an interposer or directly onto the substrate. Alternatively, these chiplets can also be stacked onto another active device chip as shown on the bottom branch. These 3D stacked dies can then be integrated onto either an interposer or a package substrate directly. As examples of 2.5D integration, redistribution layers are fabricated to connect the chips. Then one can attach the connected chips directly onto the package substrate, shown as the green block on the left. At TSMC, we call this INFO, or integrated fan-out. Or one can stack the chips onto an interposer featuring finer wiring pitch and then integrate the stack onto the package substrate. At TSMC, we call this CoWoS, chip on wafer on substrate. One can stack active chips on top of other active chips. At TSMC, we call these 3D technologies SOIC, System on Integrated Chips. Shown on the left are two examples where we stack active chips face-to-face directly onto other active chips. There are two ways to do that, chip on wafer and wafer on wafer. One can stack active dies on top of other active dies on a wafer. This is called chip on wafer. The wafer and the dies can be tested before integration, thereby improving yield. Or one can stack a wafer directly onto another wafer. This is called wafer on wafer, or WOW. For the case of wafer on wafer, the top die has to be the same size as the bottom die, and they may not be tested until after stacking. These two attributes can be constraints when considering flexibility in repartitioning and the yield of the stacked dies. Finally, if we go beyond what is commercially available today, we arrive at our vision of the next nanosystem. The 3 stands for 3D, and I believe this will be the kind of system you will see in the future. The vision is to have multiple layers of logic and memory. The memory layers span the gamut of high-speed memory to high-capacity memory. The high-capacity memory can be in 3D to achieve high memory density. The connection density for accessing the memory has to be high, otherwise memory bandwidth and latency will be a bottleneck. This is ensured by ultra-dense, fine-grained vias connecting very closely located logic and memory layers. The device technology choices shown here are just examples. There are multiple options for each of these device technologies. At this juncture, it is not important what the exact device technology is. We all have our own favorite device technology, and you will get to learn about some of them in the coming talks in this session. To summarize our vision, the future is system integration. We need more transistors, more memory, and more interconnections between the transistors and the memory optimized across the system stack for high energy efficiency. First, the number of transistors. This correlates with the peak throughput. We must increase this. This can be achieved by 2D scaling and DTCO, chip size increase, and stacking logic layers in 3D. Second, logic memory integration. Bringing memory as close to logic as possible and increasing the I/O count between logic and memory are the most important for increasing the peak bandwidth and bandwidth per watt. Again, there are many technologies from packaging to monolithic 3D integration. In fact, these technologies will increasingly blend into one another. While the current focus is on increasing the density of interlayer electrical vias, it is possible that high bandwidth, low energy communications can be achieved by other means, such as optical I/O, RF, or other coupling mechanisms. And we should be on the lookout for these other options. Third, more memory. This includes high capacity memory and also high speed memory. The more weights or data we can fit inside the on-chip memory, the less we need to go off-chip to grab data. On-chip memory can also enable compute in memory, a new way to perform computation. Finally, energy efficiency is of paramount importance. Computation energy efficiency is gated by CP² considerations that is quite fundamental. Device technologies that minimize the C and use the lowest possible V are needed. Specialized computer architecture will trade flexibility and focus all hardware resources onto very narrowly defined tasks, and by doing so will improve the energy efficiency. And this requires cross-layer optimization. Even after all the efforts to improve energy efficiency, one cannot ignore the need to dissipate the heat. Thermal solutions must be developed for the future highly and densely integrated chip. To summarize, the future is system integration. It is no longer the case that the logic transistor is the only driver for technology advances going forward. For the past 50 years, semiconductor technology development has been akin to walking inside a tunnel. The road ahead was clear, as there was a well-defined path and everyone knew what needed to be done: shrinking the transistor. Now, we are approaching the end of the tunnel. Technology development gets harder, yet the future now has many more possibilities beyond the tunnel. We are no longer bound by the confines of the tunnel. Innovation and a clear-eyed vision are necessary for continued advancement of technology that is so fundamental to the 21st century society. This is the end of my talk. Thank you for your time, and I'm happy to answer questions that you may have.
Next to the stage, DARPA Microsystems Technology Office Program Manager, Dr. Gordon Keeler.
Thank you very much. Welcome to our session on heterogeneous integration. So today we're going to hear about advances from the CHIPS program and the PIPES program. Going to talk to some of our performers and also hear from one of our transition partners that's helping to bring this technology out into the field. So if you get just one thing from my talk, I want you to know that heterogeneous integration, while it is the future, it's also today. So we've got hardware, we've got prototypes coming out of both programs. It's really going to change the way that we build systems in the future. People are adopting them already. And if you want to know more, talk to me and talk to our performers later on. Okay, so let me talk about HI in the context of our DARPA ERI investments. For a long time, we improved microelectronics performance just by following the trajectory of Moore's law. Improving geometric scaling of planar transistors gave us improvements by throwing more transistors at the problem. This became harder and harder, and so we had to look for new waves of innovation. This includes making better interconnect, new architectures, and scaling our devices into the third dimension. So these so-called second and third waves were great, but they led us to this place where we had really highly refined silicon, very expensive, sort of precise process that's very good at doing one thing, digital logic. Today, we want to find new ways of scaling. And in particular, what we're trying to do is open up this aperture, trying to move into more diverse capability. And this is heterogeneous integration, right? However, heterogeneous integration means different things to different people. So let me take a crack at telling you what's under the hood in some of our investments. So heterogeneous integration, in my mind, has three distinct facets. The first, and probably the simplest, is technology diversity. And just to be real clear, heterogeneous integration, literally, it means combining diversity. So the first type of diversity, I would argue, is technology. It talks about putting together different capabilities from different foundries, different technology nodes, and is exemplified by our CHIPS program. If that's about improving digital logic, the next step up this ladder is functional diversity. This is sort of the more than Moore approach to scaling. And so we've got programs like PIPES and T-Music that are looking to bring different kinds of capability into the package. In particular, analog, RF, mixed signal, photonics, and MEMS. The third type of diversity, probably the hardest to do, is really this 3D HI type. It's bringing new materials to this specialized platform to create capabilities that we can't do with the materials we've got today. In particular, this is important for digital logic, for better memory on chip, and for improving integrated photonics. Our programs 3D SOC, Frank, and LUMOS are great examples of these kinds of investments. You'll hear about some of these programs next. So let me start with the CHIPS program. CHIPS is probably our oldest ERI program, It's about 2 years in. We actually just entered phase 2. CHIPS started with the observation that the cost of designing in and fabricating in the most advanced technology nodes had become so high that it actually priced out all but the high-volume commercial users. This is a big problem for the DoD, where we want to be working at these advanced nodes. And so CHIPS made the observation that maybe what we could do, rather than making one big monolithic piece of silicon, is compose a system with modular chiplets. The idea of chiplets to build systems has actually taken off like wildfire in the community. And so commercially, all the big players are doing this today. Under CHIPS, our performers have been working on the 3 pillars that make this possible. The first is creating a large and capable set of chiplets. The second, working on the assembly and packaging technology so that you can have high-density, high-yield systems built out of chiplets. And then the third is really working on this ecosystem. The ecosystem requires everybody to work together, and so it means we have to have sort of standards and efficient interfaces to compose these systems. The second program you'll hear about is PIPES, Photonics in the Package for Extreme Scalability. So when you get bigger and better systems in a package, and you build a system with a bunch of them, the bottleneck becomes not necessarily the ability to do compute in that package, but our ability to move data from one point to another. Now, we already know that optics is great for moving data long distances, but when you have to move from a package across a board to a transceiver, you've lost most of that performance improvement already. So PIPES is looking at putting photonics into the package. We're in phase 1, we're about 1 year in, and we've made big strides. Some of our performers, and you'll hear more about this today, are making advanced multi-chip modules with photonic I/O. We have other performers working on the component technologies, better integrated photonics, multi-wavelength sources, and really small switches so that we can do switching in the optical domain. And finally, the LUMOS program. This is an example of that materials diversity that I talked about. We've got silicon photonics, which really allows you to scale our systems really well. Integrated photonics manufacturing is great on the silicon platform. However, it lacks optical gain. And that means that we can't scale our systems the way that we want to. Optical gain is typically found in 3-5 compound semiconductor materials. So LUMOS is about bringing these systems together for best of both worlds. If successful, this will allow us to scale photonic solutions in the future, particularly in complexity, so we can make optical neuromorphic computing and things like that. In power, so that we can have better sensors and microwave photonics. And in spectrum, so that we can build quantum and atomic systems. All right, so let me set up the rest of the session today. You're going to hear highlights from the CHIPS and PIPES programs, particularly from Sergey Shumarayev at Intel. The Intel team has been working on CHIPS, and they've been integrating their advanced digital microelectronics with new capabilities. They've been adding RF data converters, photonic I/O, and small accelerator chiplets to do machine learning and DSP. You'll hear from Mark Wade at Ayar Labs about the PIPES program. Mark and his team have been working on photonic solutions, on pipes and other programs before that. And so Mark will talk about some of the technologies that go into enabling this capability. And then finally, you'll hear from Brett Hamilton at OUSD R&E. Brett is a transition partner, and he's the program manager for the Navy SHIP program, which is looking to develop onshore assembly technologies to help transition these out into the field. Okay, so let me close with this. The path to DoD impact for 3D-HI is the following. Right, DARPA is working on these disruptive capabilities, some of the ones I talked about, better performing components, adding RF and photonics to the package. And our performers are doing that, but they're also trying to do it in an accessible way. And we do this by creating open source technologies, by creating automated IP generation tools so that you can port things to new foundries, and providing access to advanced technologies. This is a great example of this is a new ERI defense applications program Tim Hancock just kicked off with Raytheon, where they're taking the prototype hardware coming out of the CHIPS program and applying it to real-world applications. So finally, we're working closely with our transition partners like Brett and others at the Pentagon to make sure that the the users and the applications have access to domestic foundries and advanced packaging tools that we can really get this stuff out into the field. So with that, let me introduce the first speaker, Sergey Shumarayev from Intel Federal.
Good morning, everyone. What I would like to share with you today is our chiplet integration results, as well as the road ahead of us. For our motivation, we are going back to Moore's original paper, where on page 3, Gordon points out that packaging offers another vector for advanced scaling. So let's examine that vector. With the help of high-density packaging technology, we've been exploring heterogeneous integration across several programs. First, starting with chips, where we offered our commercial FPGA platform for integration and research across diversity of academia, commercial, and defense industrial-based customers. This allowed us to forge key partnerships to select best-of-breed technology and to grow our chiplet ecosystem in HiCube and in pipes. Let's take a closer look at CHIPS Phase 1 results. As you can see, Stratix 10 FPGA platform enabled heterogeneous integration of 7 chiplets across 5 technology nodes, which were manufactured in 3 foundries. What all of these chiplets had in common was AIB interface. AIB interface is used across Intel's commercial FPGA families. In chips, Intel open-sourced AIB. AIB is now available from 3 sources: Synopsys, Intrinsics, and Blue Cheetah. Furthermore, Blue Cheetah created AIB generator software. 4 Keeler demonstrations were made possible in CHIPS Phase 1. Picture on the left shows RF demo board, which was used to demonstrate direct RF converters plus FPGA that was done in partnership with Ayar technology. Now this is transitioning to our products. And this platform was also used to enable University of Michigan DNN ASIC research into the acceleration of load from FPGA. On the right-hand side, you can see optical-enabled FPGA demonstration platform. This demo established baseline for our new area of optical connectivity that we are exploring in the PIPES program. Same platform was also used to prove our AIB generator in partnership with the Blue Cheetah. For those who are interested in AIB specifications, please follow the link below. HiCube program is also known as Domestic Foundry. It stands for the Heterogeneous Integration Incorporating Intel. Our intention is to offer a full domestic manufacturing ecosystem, which is based on Intel's 22FFL technology node. 22FFL is using 40nm FinFET transistors, but without the expense of back-end double patterning. As a result, you get best cost performance product. As we work with our partners to architect their full solution from silicon through multi-chip package design all the way to the demo systems, we are able to leverage our full portfolio of commercial chiplets. In our initial engagement, we partnered with University of Berkeley and University of Michigan to enable their research, and now we are partnered with 3 defense industrial-based partners to facilitate their value-add chiplet creation. Let's review connectivity figure of merit. This chart is a courtesy of Gordon Keeler. Figure of merit of interest on a y-axis here is the product of bandwidth density as expressed by the shoreline bandwidth in the gigabits of data that you transmit on a millimeter of a shoreline, and the energy efficiency with which you can transmit this data. Energy efficiency is expressed in a picojoule of power consumed per bit of data transmitted. As a result, the higher the number on this chart, the better the figure of merit, because you provide the highest bandwidth density at the lowest power possible. And on this chart, DARPA tabulated the best published data for in-package I/O, on-board connectivity, and off-board solution, and expressed that figure of merit as a function of distance each entry can supply. Clearly, in-package I/O offers the best figure of merit, but for a very limited physical distance. Figure of merit rapidly deteriorates, notice the log scale here, as the communication distance increases from in-package to on-board and to the off-board solution. PIPES programs was established to break through this well-known I/O paradigm. In our 2020 CHIPS demonstration, for example, we've combined direct digital I/O signaling via AIB with the optical to offer a figure of merit on the top right corner of this chart. As we move across pipe phases, with each phase, we intend to advance optical technology offering in combination with the next generation AIB interface so that we can raise the bar of a connectivity figure of merit, as shown on this chart for each phase. As we reflect on our last year results, I would like also to take a moment to set 1 year look-ahead expectation for each program. Let's start with chips. In chips, you should expect to see the details and results of a new partnership as we grow our chiplet portfolio, both commercially and with academia. We will also develop and test next generation AIB and EMIB to be leveraged across the follow-on programs. In HICube, jointly with University of Berkeley and University of Michigan, we will finish post-silicon learning. We will work with our defense industrial base to get them through silicon tape-out, multi-chip package silicon bring-up to enable deep specific demonstration. Finally, in pipes, as we focus to bring the new area of connectivity, we will also intend to look into the optical high-volume manufacturing and automation. This will be done in partnership with Tyndall and Ficontech. You should also expect to see first 10 terabit optical MCP, and we will leverage that MCP to study optical systems as we work with our defense industrial base in partnership with Raytheon, NGC, Lockheed, and LPS. Of our overall chiplet portfolio. While I'm not going to go through each entry in the table on the left-hand side, I would like you to take a look at the process column. As you can see, our solution is both technology and foundry agnostic. In a summary, what you can see here is the 3 FPGA families, each FPGA family with multiple devices. What you can also see here is the 6 SerDes chiplets, 3 data converter chiplets, 3 optical chiplets, 2 ASIC compute chiplets, 4 university research chiplet, 1 deep research chiplet, and finally 1 Intel eASIC chiplet. In summary, across the programs, what we have here is integration platform portfolio with the plan for 20 chiplets and 3 FPGA families that are done on 11 process nodes across 3 foundries. This is done in a broad partnership across industry and academia to produce the killer applications in a fraction of the development time and cost. Your chiplet can be here. If you are interested, please follow the link provided in this presentation to learn about our technology offerings, ask questions, and hopefully to join our journey. Thank you for your attention, and I hope to engage with you on this exciting journey.
Hi, my name is Mark Wade, and I'm the president and CTO of Ayar Labs. And today, I'm excited to talk about work that we've been doing on the DARPA CHIPS program, which is a program looking at bringing photonics in the package for extreme scalability. As my colleague presented in the previous talk, the DARPA CHIPS program aims to use heterogeneous integration to bring about disruptive innovation to semiconductor technologies, while requiring a fraction of the time and the cost of traditional advanced node CMOS development. So I wanted to start by showing an example timeline from our own experience using the CHIPS platform and the chiplet ecosystem to bring a new generation of optical technologies inside the SoC package, resulting in a breakthrough in high bandwidth chip-to-chip communications. In July of 2019, at the ERI Summit, Intel announced that we were working to build an optically enabled FPGA by integrating optical chiplets with a state-of-the-art Intel FPGA. Ayar Labs taped out its chiplet in August of 2019, and by early January of 2020, Intel and Ayar Labs assembled the optical FPGA demo platform. And by late January, we achieved a first-of-its-kind demonstration with Intel's FPGA using the Ayar Labs optical chiplet for optical I/O directly from the SoC package. This achievement leapfrogs current I/O technologies and provides unprecedented improvements in bandwidth, energy efficiency, and reach. And all in all, it took about 5 months from GDS submission to demonstration, which shows how heterogeneous integration leads to rapid innovation. The previous talks did an excellent job explaining the challenges surrounding chip-to-chip I/O and why a new optical technology is needed to solve these challenges. Through the DARPA CHIPS and DARPA PIPES programs, we've been able to show a compelling path forward, that uses optical chiplets heterogeneously integrated in the same package as an advanced SoC. And these demonstrations set the stage for all advanced SoCs to have access to optical I/O. Now, once optical I/O becomes a reality, there are incredible opportunities to architect systems that were previously not possible. And by breaking the traditional bandwidth distance trade-off, we can now disaggregate resources, compute, memory, sensors, actuators, and storage, and connect all of these different chips together with a high-performance optical fabric. The bandwidth, latency, and power of the optical fabric enables much larger compute nodes to be built, where a node can now be thought of as a rack or multiple racks of servers. And by building larger and larger compute nodes with things like unified memory access, these have exciting implications in areas such as machine learning and artificial intelligence, where training bigger and bigger neural nets leads to exciting advances across many application areas. Now, let's take a closer look at the underlying technology. Our approach is to monolithically integrate silicon photonics devices and MOSFET transistors onto the same piece of silicon. And we can build silicon photonics devices such as waveguides, modulators, and photodetectors with the same materials that are used to build advanced MOSFET transistors. And by densely integrating photonics devices alongside transistors, we can build optical chiplets that have millions of transistors and hundreds of optical devices on the same chip. And since we are using standard SY CMOS technologies, we're able to build these chips in a state-of-the-art high-volume 300mm CMOS foundry. This slide shows an image of the 300mm wafer with our TERAPHY, short for terabit phi, prototype chiplets. These chips have an AIB electrical interface on the left, an electrical crossbar that does the channel mapping between the AIB interface and the TERAPHY optical macros, and an array of optical input-output structures to connect to all of the optical fibers. This TERAPHY chiplet immediately shows the power of our approach. Each TERAPHY chiplet supports up to 2 terabits per second per chiplet, and by integrating multiple TERAPHY chiplets into an SoC package, the equivalent of up to 768 PCIe Gen 4 or 5 lanes per socket can be supported. We've built multiple form factors to support both single die package and multi-chip package testing. The single die package form factor allows testing, characterization, and evaluation of the TERAPHY optical I/O chiplet. And we're making these available for customers and partners to evaluate the TERAPHY technology to better understand how it can impact their applications. The same TERAPHY chiplets can be co-packaged with a variety of SoCs, and right now the multi-chip package evaluation board has been developed in partnership with Intel, as previously discussed. We view the transition to optical I/O as a multifaceted paradigm shift that will have far-reaching implications. To achieve this, it begins with low-level innovation at the device level, but much more is required to actually result in a ubiquitous technology. Devices need to be integrated with high-performance electronics, and this must be done in such a way that is compatible with high-volume CMOS manufacturing. It doesn't stop with the CMOS wafer, though. We have to build the technology in a way that is compatible with scalable packaging techniques, especially with the new addition of bringing optical fibers directly to the SoC package. Optical I/O also needs lasers to power up their communication links, and a new class of multi-wavelength lasers is needed. And last but not least, we need a robust ecosystem to coalesce around every piece. And we need to standardize the appropriate elements of the solution to create a robust group of technology suppliers. With the advances we've made to build a new generation of optical I/O technologies, and through the partnership with DARPA and with Intel, we believe a new era of connectivity and system architecture is here. Ayar Labs is now sampling prototype TERAPHY chiplets with eval boards, software and firmware, and detailed user guides and integration guides. And we're now making these eval kits available to our customers and our partners so that you can get your hands on this breakthrough technology and test it out in your own labs and environments to start to better understand how the paradigm shift to optical I/O-based solutions can bring transformative value to your own applications. We also think it's imperative that we work on building a domestic ecosystem that can scale the manufacturing, assembly, and testing of these solutions so that end customers and system integrators can more easily access the technology. Now, be sure to check out our video of the live running demo, And also come by our poster session where I'll be answering any questions that you may have live. And please don't hesitate to contact us if you'd like to get more information. And you can contact the email address shown here on the screen. And with that, thank you for your time, and we look forward to hearing from you.
Hello, my name is Brett Hamilton. I'm the Principal Technical Execution Lead for Advanced Packaging for OUSD R&E for the Trusted and Assured Microelectronics program. And today I'm going to be talking about some of our efforts to advance state-of-the-art in advanced packaging. In particular, I'm going to be talking about state-of-the-art heterogeneous integration into packaging. It's a program that we initiated about 8 months ago called SHIP, and I'll be discussing some of the details of that and what we hope to accomplish through that program. So DoD has a lot of efforts going on in the area of modernization, and all these efforts require access to state-of-the-art advanced microelectronics. And there are several factors that drive this. One is the extremely high processing requirements, the restrictions in size, weight, and power. And if, for example, you look at the instrument bay in an aircraft carrier here on the right of the screen, you can see there's not much area in there. And when I go out and talk to programs, they're basically telling me we need to put more processing power in that same swap area. And to do that requires making things smaller and better and faster. We need to move terabytes of data. We're doing a lot of RF digitalization now and generating huge amounts, terabytes of data in real time that has to be distributed to the various system elements. We need to be able to leverage commercial state-of-the-art, yet customize and optimize for DoD applications. And then, of course, we have to meet the DoD reliability requirements and the cost and schedule for our DoD programs. So heterogeneous integration and advanced packaging helps address all these challenges. So when we first started the SHIP program, we weren't sure if we needed to have a digital focus area and an RF focus area. So during our market research, it became clear that the technology drivers for digital is a lot different than that for RF. And if you look, for example, in the area of digital, it's all about high-speed interconnects. How can you move data across from one chip to another or within a chip very efficiently at a low power rate? So the digital focus is on these high-speed interconnects, such as this embedded interposer, silicon interposer in this organic substrate here in this cartoon. And that enables very efficient signal transmission, basically in the picojoules per bit. And that's really important. That's almost as good as a monolithic ASIC. So that's what is really driving this. And these have thousands, 4,000 or 5,000 interconnects through these interposers. Whereas on the RF side, it's all about balancing RF performance versus maturity of various technologies. So it's a lot more mixing and matching of different kinds of semiconductors to address things like high power. There's a lot of issues with thermal, and it's really focusing on high efficiency RF transmission lines. So it's a lot of different materials and things used there. So we decided, based on all that, to go with a SHIP digital and a SHIP RF focus rather than trying to combine it into one. So starting in around October of last year, we kicked off phase 1 of the SHIP program, and it was an OTA through the SMARTS OTA program that was advertised. Phase 1 was to go out and develop the technical capability and the business plan for a sustainable, basically domestic manufacturing capability that was secure and reliable for advanced heterogeneous integration, packaging, and test that could support the military and aerospace community. And there were two main areas under that, the design center and the assembly and test center. In phase one, under the digital area, the two performers were Xilinx and Intel Federal. In RF for phase one, it was Keysight Technologies, Qorvo, GE Research, and Northrop Grumman. So where we are now in the program is we finished up phase one, we've received those reports and deliverables, and we're in the process of doing a down select for phase two, which will kick off hopefully here in about 3 or 4 weeks. Phase two then goes for a couple years, basically to stand up the capability and start doing prototype designs to mature the process and flow. During that period, we'll be working with the DIB partners to select demonstrator prototypes that is going to be based largely on actual program needs. So when we do these demonstrators, it's not just a proof of concept, it's also something that once it's finished could be transitioned directly to a program. That goes for a couple years and will be at initial operating condition at the end of that, and then another year or two to get to a full operating condition. This is a pretty aggressive schedule, but because we're leveraging existing commercial technology as best we can, we think it's reasonable, although still quite aggressive. So basically, heterogeneous integration and advanced packaging enables the DoD programs to leverage the best of commercial technology while creating unique custom ASICs that can optimize for their particular application, and being able to mix these chiplets in a heterogeneous integrated package is a very powerful capability compared to trying to do monolithic ASICs, the cost of which at state-of-the-art is just so prohibitive that there are very few programs that can afford to do that. But if we leverage state-of-the-art that's investing billions in their high-end processors or FPGAs, and then combine them with these custom chiplets that we can go out and work with the DIB to develop, that gives us a very optimized solution that can transition quickly into DoD programs. So I'm very excited about the DARPA programs that have really been the trailblazer for this SHIP effort, in particular the previous briefers, the chips, the pipes, HI3, all those programs have really enabled a critical transition path of that technology that went from proof of principle during those programs into the SHIP program, and it's made standing up SHIP a lot easier because we had that history and that effort, and it really helped minimize the risk of it as well. So, I'm very thankful for DARPA, and we're continuing to work together. A lot of those programs are still ongoing. So one of the other important aspects of this is we have to continue to keep the evolution going and staying on this commercial path. So right now the focus is mostly on 2.5D, but we're also looking at 3D, and then as commercial keeps moving the bar, we want to be as close to that as we can on our DoD systems so that we can leverage the best, which is really going to be important for these new systems that need AI, autonomy, cognitive EW, and the list goes on and on, where we really need this high processing power. So there at the bottom here are just some other workshops and demos related to this throughout this workshop. So I would encourage you to go out and check those out. Thank you.
Now joining us, professor at the University of California, Los Angeles, Dr. Jason Wu.
Good afternoon. I would like to talk about 3D heterogeneous integration and the future of data-centric computing. High-performance digital systems have seen phenomenal improvement over the past 50 years thanks to transistor miniaturization per Moore's law, and in the case of CMOS VLSI, the Donut scaling theory. As can be seen, we now have over 10 billion transistors in a microprocessor with tremendous computational throughput. However, since the mid-2000s, the clock rate has been set at 2 to 3 GHz, mainly limited by the power constraint of 1 to 200 watts per microprocessor. This is due to the inability to lower the switching energy of the transistors as device scale below 45 nanometer following the Dennard scaling theory. In addition, in order to take advantage of the very large number of transistors available per chip, multi-core architecture has been adopted. Sub-45 nanometer transistor switching energies cannot be scaled following the Dennard scaling theory is due to the inability to reduce the power supplied VDD, as can be seen here over the years. This is due to the finite on-off characteristic of a MOS transistor limited to larger than 60 mV per decade I at room temperature. As a result, to maintain an acceptable static power, yet with good switching speed for a few gigahertz clock rate, VDD cannot be scaled much below about 0.7 volt at room temperature. To overcome the VDD scaling limit, novel devices based on alternative switching mechanisms such as quantum mechanical tunneling, magnetic, and superconductor junctions has been proposed and examined in many current and earlier DARPA programs. However, by far, the fastest switching devices today is still deeply scaled CMOS. In addition, the novel devices are unlikely to achieve the VLSI density necessary for many HPC digital systems. One way to break the VDD scaling limit is to operate VLSI at cryogenic temperatures, and therefore has gained much renewed interest recently. Another roadblock for advanced HPC digital system is the memory bottleneck. High and high memory bandwidth is needed with increasing microprocessor computational throughput, particularly when multi-thread architecture is used. Also, there is a gap between the memory and the logic scaling in the last 15 years, further hampering the data bandwidth needed between the logic and the memory. As a result, memory bandwidth is increasingly limiting the overall performance HPC digital systems. Therefore, in order to further advance high-performance computing digital systems, we need deeply scaled devices with very low power and high-performance switches, with low operating voltages, high current densities, high ion current, and low I-off. We also need fast and high-density memory with large array size of very small footprint cells, and we need it to be very fast, short, and read time. We also need next-generation computing architecture merging in order to increase the data rate between the data processing and the memory by merging computing within memory and heterogeneously integrate diverse accelerators within the microprocessors. One of the ERI efforts addressing these challenges is the 3D SoC program. By heterogeneously integrating CMOS logic with dense array of RRAM memory and also CNT-based switches, which is supposedly to be very, very low power, very high-performance, no-power computing system can be realized. The program has already achieved very impressive results in the phase 1 efforts, such the first demonstration of RRAM process in the US foundry. They have developed CAD tools for this 3D integration platform and also use it to design microprocessors. In addition, carbon nanotube fab process has been developed at a commercial foundry, SkyWater. Many companies have indicated their interest in using this 3D platform for their systems. Professor Shulaker will detail these results and talk about their phase 2 efforts as well as technology transfer path. Thank you.
Today I am so honored and excited to be able to share with you all the great progress that we've been making in the 3D SoC program. And before I begin, I want to extend my deep gratitude to the government team for both their support as well as constant guidance on this ambitious DARPA hard program. And of course, I'm here speaking on behalf of a tremendous group of folks who have all partnered together to try to transform what many thought of as a dream into a reality. It's an honor to be leading this program at MIT alongside the Dean of our School of Engineering, Professor Kazior. I'm also deeply thankful to be able to work alongside my original PhD advisors, actually, who remain advisors to this day, and who really are responsible for the genesis of so much of what you'll hear about today, Professors Subhashis Mitra and Philip Wong of Stanford University, alongside Professor Simon Wong and now Boris Merman of Stanford as well. And we are tremendously excited to be partnering with Skywater Technologies, a US DMEA trusted foundry based in Minneapolis, the work there being led by Dr. Brad Ferguson and Mark Nelson, which brings a powerful combination of foundry capabilities with expertise in advanced technology development. And of course, over on the right, you see all the remarkable students who are really the ones responsible for making all the progress I'll be sharing with you possible. They literally represent the future of US microelectronics. So without further ado, the goal of 3D SoC is to transform a conventional 2D system today, which has limited connectivity and thus bottlenecks between separate off-chip memory and on-chip compute, into the following: a monolithic three-dimensional integrated circuit where we integrate an entire system into a single chip. So we have multiple layers of compute fabricated directly on top of one another, interleaved with layers of memory, all densely integrated within this 3D stack with conventional back-end-of-the-line nanoscale interlayer vias, truly embodying computation finely immersed with memory, all within the same chip. And this is a big if, but if one could realize such a monolithic 3D system with dense and fine-grained integration of logic and memory, the potential benefits are significant, which makes all the hard work developing this technology worthwhile. It's projected that even when implemented at a relaxed 90 nanometer technology node, that such 3D SoCs can achieve over a 50x benefit in energy efficiency versus a conventional 2D chip implemented in state-of-the-art silicon CMOS at an advanced node for the most challenging and exciting and impactful next-generation future big and abundant data applications. And while the promise of 3D SoC is exciting, the most exciting part of this, and this is actually the punchline of this entire talk, is that we can and are building such 3D SoCs already here within the US today. Here you can actually see an engineer within the foundry at Skywater Technologies standing next to the piece of equipment that we actually use to deposit carbon nanotubes during the manufacturing of our 3D SoC wafers. And in fact, here's a photograph of one of the many, easily hundreds, perhaps thousands by now, of completed 3D SoC wafers we fabricated during the program. And if we were to crack open this wafer and zoom in on a scanning electron microscope at that cross-section, you can actually see the many vertical tiers of metal routing and compute and memory and more metal routing fabricated one on top of the other, forming the full 3D SoC. So I want to stress straight from the beginning, this is very real now. Here are the actual wafers. And the reason why the rest of this talk matters to you, and to you personally, is because our aim in 3D SoC is not just research some new technologies for research's sake. Our goal from the very beginning was to establish these new technologies and offerings within a US foundry, so all of you folks would be able to use and benefit from it. And I'm very excited to announce for the first time that we will be launching an early adoption program, which allows you folks in the broader community to design, tape out, and test your very own 3D SoCs. So if you're interested, I encourage you to go to this website for more information, and please feel free to reach out and keep your eyes open for further announcements that we'll be making in the near future. So for the rest of this talk, let me tell you what will actually go into these chips that you'll one day be able to tape out yourselves. And I'll try to go into a little of actual detail to show you how we actually make these 3D SoCs in the foundry today. So let's enter the technology deep dive. So to build these new 3D SoCs, we have to use new technologies that we can fabricate at low temperatures in the back end of line. For logic, we'll be using carbon nanotubes, and for memory, we're using RM. So let me take these each in turn, starting with the carbon nanotubes. So a carbon nanotube, if you remember, is essentially a rolled up sheet of graphene forming a nanocylinder with a diameter of around 1.2 nanometers. A carbon nanotube field effect transistor, or a CN-FET, is formed by using the CNTs as the channel of the transistor with traditional lithographically defined source and drain metal contacts with a conventional high K metal gate stack. Now the motivation for using CNTs for the compute within our 3D SoC comes from many sources. I've listed 3 here, but by no means is this list exhaustive. So first, we want to choose a technology which is itself energy efficient, and it's projected that if you could build a working chip from CNTs, that chip would achieve around a 10x, an order of magnitude benefit in energy efficiency versus the exact same chip made at the exact same node made from silicon FETs. But more importantly, we can fabricate CN-FETs at low temperature, which enables us to naturally build them in the back end of the line to realize our monolithic 3D systems, providing further benefits in addition to these device-level benefits I just mentioned. And thirdly, while not what I'll be focusing on today, but a very important but more nuanced point, is that these benefits are just the beginning. Because once we can establish a working CN-FET technology, it can provide a roadmap for decades worth of future benefits by enabling continued scaling to aggressive future nodes. So for instance, once we establish 3D SoC at a 90 nanometer technology node, providing that initial 50x benefit, we can leverage known Dennard scaling to continue to get further benefits well into the future. So 3D SoC is just the beginning. But of course, despite this promise, there is always a catch. And the catch here is that there are some very real serious challenges ranging from material level defects to manufacturing challenges that have prohibited realizing large-scale systems using these new technologies in the past. And at the last ERI symposium, I showed you some key breakthroughs which for the first time overcame all these challenges, enabling us to realize actual systems using CN-FETs. And for the sake of time, I won't go through the details here, but these new techniques span the entire system stack, from low-level material innovation, like developing new solutions of CNTs with record purity, so pure in fact that they meet the strict chemical contaminant requirements for introducing these new materials within commercial silicon CMOS manufacturing facilities, to new processing techniques, such as developing robust methods for realizing CMOS or complementary CN-FETs, to new circuit design techniques, which allow us to design circuits in such a way that make them completely immune to material level imperfections, like the presence of metallic carbon nanotubes, to new manufacturing methodologies for developing new approaches that address key feasibility concerns, such as decreasing cost of ownership and increasing wafer throughput. And to demonstrate that these approaches really do work, we use them to fabricate at MIT the most complex systems ever made with any beyond silicon emerging nanotechnology, such as a three-dimensional monolithic imager with in-situ image processing, to complete SRAM memory arrays, and culminating in a commercial-grade 16-bit microprocessor fabricated entirely from CN-FET CMOS. But of course, there is still a big disconnect that often exists between realizing a technology in an academic lab versus meeting all of the additional constraints for establishing a new technology offering in a commercial foundry. And I'm excited to share with you that since that last ERI symposium, we've been able to establish this full CN-FET CMOS process flow within the foundry, to the point where we can take that exact same RISC-V microprocessor we built in our academic lab at MIT, and can now, and have built, that exact same chip, but now at a 90 nanometer node in the foundry at Skywater. And obviously, there's a lot of things that needed to happen to get from the lab to the fab. So I thought I'd take a few minutes and pull the covers back, so to speak, and actually share with you some of the steps and tricks we've developed to bring this technology from the lab to the actual fab. Okay, so it immediately begins with a major problem. How do we get these nanotubes on our wafer? So we do this now entirely within the foundry, using a fully automated process that runs on batches of industry standard 200mm wafers. And here you see the piece of equipment with one of my students and a Skywater engineer next to it, which deposits the CNTs, which are suspended within a solvent solution uniformly across the wafers. And with careful engineering and tricks, we've developed ways to speed up this process from taking several days to several minutes, a speed up of over 3 orders of magnitude. And here you can see SEM images of the CNTs deposited in a uniform monolayer across the entire wafer surfaces. Okay, so once we have our CNTs on a wafer, we then need to build our devices. So let me show you how we actually build the CNFETs within the foundries. So if we zoom into a wafer onto, let's say, a pair of CNFETs, we would start with these embedded metal gates in the wafer, and then we deposit our high-K gate dielectric, followed by the solution-based CNT deposition I just showed you previously. And this is actually a critical step, because the solution-based deposition is room temperature, which decouples the high-temperature CNT synthesis from the 3D SOC wafer, enabling the entire CNFET process to be all low temperature, and therefore back-in-line compatible. Okay, we then deposit our metal source and drain contacts, and to form CMOS, or complementary N-type and P-type CNFETs, we developed a 2-step dual doping process. It begins with work function engineering, where we use 2 different metals to form the NMOS and PMOS CNFETs. And then we use electrostatic doping by encapsulating the devices in different oxides to perform the final tuning of the threshold voltages to form, for instance, either a low power, low leakage technology, or let's say a high performance, faster technology. And through this process, we can now reliably and reproducibly realize symmetric P-type and N-type CNFETs. But of course, it's not enough to build just one CNFET. In a foundry, you need to be able to reproducibly and consistently fabricate wafer after wafer after wafer. So we've optimized the process to the point where we can do just that. We can now fabricate a wafer and measure dies distributed across this entire wafer surface, and then we can redo that for many wafers, one after the other. So the standard which I'll show you for the first time is for multiple dies across multiple wafers, and we've not excluded any devices from these measurements for any reason whatsoever. And here are some of the results to give you an idea of the level of control and reliability we've been able to establish within the foundry for this emerging nanotechnology. So every tiny colored pixel here on that wafer map, which you can't resolve by your eye, corresponds to the physical location of a CNFET, and its color corresponds to its threshold voltage. And these are the distributions down below. You can actually see across both intra and intra-wafer, the process is highly reliable and reproducible. These results are showing over tens of thousands of CNFETs without any outliers removed for any reason. And now that we can reproducibly fabricate devices, we can now move to fabricating actual logic gates, the building blocks for our chips. We first designed thousands of different logic gates, forming an entire standard cell library. Here I'm showing you just 15 of them for clarity. We then fabricate each and every one of these standard logic gates. Here you see the SEM images of those fabricated gates. And then we experimentally measure and validate each and every one so that you folks can use them when you design your very own chips. And I'll speak more about that shortly. Okay, now that we can make 2D chips, we can now seamlessly move to making 3D chips as the CNFETs naturally enable monolithic 3D integration. So we can fabricate CNFET CMOS on the bottom layer of a chip, and then seamlessly we can fabricate another layer of CNFET CMOS directly on top. and we can repeat this for as many times as we want. These aren't just cartoons. You can actually see a cross-section SEM of the CN FETs in series fabricated directly overlapping on top of one another. Here's a top-down SEM showing the CNTs bridging those series CN FET source and drain metal contacts. And here are some actual measured CN FETs, illustrating that the CN FET performance for both the PMOS and the NMOS CN FETs is invariant to whichever layer of the 3D chip they're fabricated on. Now, you might be wondering, maybe Max is hiding something here in the data because this is on a linear scale. So here are the same devices plotted on log scale as well, confirming statistically similar performance of the devices across arbitrary layers of the 3D stack. And lastly, we can combine all of this together, and you can see how we can get all the way from CNTs all the way to realizing our 3D SoC systems. So here again, you can see that RISC-V fabricated within the foundry, and not only is it a RISC-V microprocessor fabricated from CN FETs, a first for an emerging nanotechnology, but it is also the first microprocessor ever fabricated completely within the back end of line in 3D. So in the bottom right on this slide, you can actually see the 3D rendered GDS of the actual RISC-V that was fabricated, which highlights its three-dimensional aspect, where the transistors are actually fabricated not on the bottom, but in the middle of the chip, with metal routing both above and below them. So there's a lot of information there, but I want to make sure that you take away the following 3 key points. Point number 1, everything is wafer scale at industry standard 200 millimeter wafers. So there's no pre-net customization of any sort during design or processing. Point number 2, everything is silicon CMOS compatible, processing and design. We use the exact same design tools and the exact same equipment within existing silicon foundries that are currently fabricating silicon product wafers to fabricate our 3D SoC wafers. And this compatibility with existing silicon infrastructure is extremely important when considering adopting new technologies. And point number 3, this is achievable today. So now on to the resistive RAM, or RRAM. So as a quick reminder, RRAM is a non-volatile, high-density memory which can either form or destroy a conductive filament between 2 metal electrodes to program it into either a high or low resistance state. At the last ERI symposium, the Stanford team showed several key breakthroughs on this RRAM technology, including the first multi-bit per cell RRAM systems, complete non-volatile IoT processors that, thanks to the RRAM, could achieve over a 10x improvement in battery life, demonstrated in actual hardware, as well as new algorithms that overcame limited RRAM endurance to demonstrate the ability to achieve over 10-year operation even for challenging applications like continuous AI inferences. So the big question now is, how can we fit something like 4 gigabytes of memory on chip? And for comparison, at the same 90 nanometer technology node, you're looking at the ability to fit only megabytes worth of SRAM on chip today. Well, let's take a look at a conventional RRAM cell. So a conventional RRAM is fabricated in a 1 transistor, 1 RRAM cell, or 1T, 1R, whereby the footprint of a single RRAM cell is dominated by the footprint of a transistor that's used as its selector. And it's arranged in this crossbar configuration, as shown in the schematic. So to increase the density, we can try to squeeze more RRAM within the footprint of that single select transistor. So for instance, you can go from fitting 1 RRAM cell within the footprint of a select transistor to squeezing more RRAM within the footprint of that single select transistor. So here, this is a schematic of a 1T 4R cell, whereby we fabricate multiple RRAM over the same single select transistor, fitting 4 RRAM within that footprint area. And the Stanford team said, well, why stop there? To increase the density even more, they leveraged the 3D integration capabilities of RRAM to fabricate multiple tiers of RRAM over the same select transistor, so now fitting 8 RRAM within that same footprint. And they combined their first demonstration of multi-bits per cell with multi-RRAM per transistor, demonstrating for the first time at a full array scale multi-bit per cell 1T8R full memory arrays. And to emphasize this point, and this is a very important point, none of these are just cartoons or fanciful ideas. Each and every one of these tricks have been established experimentally within the US foundry at SkyWater. Here you see the cross-section SEM of a three-dimensional 1T8R RRAM cell. And here you see the experimental measurements of RRAM resistance values being programmed into 16 distinct levels, equivalent to storing an impressive 4 bits per cell. And combining these two approaches gives multiplicative benefits in the on-chip RRAM density you can achieve. And of course, this is only possible thanks to the unique tricks the Stanford team developed, leveraging everything from new circuit and integration schemes to clever new programming algorithms. And I encourage you to check out their recent 2019 IDM paper, which goes through all of this in great detail. And when you multiply the effects of the first 1T8R memory arrays with the 4 bits per cell, with the ability to integrate the select transistor, in this instance the CNFETs, all within the back end of line, we are on a concrete path in 3D SoC for achieving that target of gigabytes of on-chip non-volatile memory entirely within the back end of line, despite it being implemented at a relaxed 90 nanometer technology node. So I hope I've been able to show you thus far that we can build these 3D SoCs. But what about designing a 3D SoC? After all, once you develop the ability to fabricate 3D SoCs, for you to make use of it, you have to be able to design with it. So as part of 3D SoC, we have also completed and developed the entire design infrastructure, starting at the lowest level with compact models calibrated to experimentally fabricate devices from the foundry. And these models are fed into a commercial-grade process design kit, or PDK, which we've developed, which includes monolithic 3D design rule checkers, monolithic 3D layout for schematic checkers, monolithic 3D test extraction, monolithic 3D place and route, and so on and so forth, to enable And to enable designers to design with this technology, it also includes thousands of standard cells forming a complete standard cell library, some of which I showed you before, and each of which have been experimentally fabricated and validated already today. And it doesn't stop there. We also have the entire design flow, leveraging industry standard design tools with very minor modifications, which perform logic synthesis, OPC, metal dummy fills, etc., enabling a designer with a click of the mouse to go from high-level description like RTL all the way to the final masks used by the foundry to manufacture these wafers. And then a few months later, you get your monolithic 3D wafers fabricated with CNFETs and RRAM. So what's next? Well, moving forwards, our aim is to continue to develop and optimize the processing, continue to add to the design infrastructure, so that combined, at the end of the day, there will be a technology from a US foundry that can be leveraged by you, the broader community. And the ability to begin to engage with all of you is really the most exciting next step in this process. Because owing to the great flexibility that a technology like 3D SoC represents, the more people who engage in this will mean the more application spaces 3D SoC can be applied to. It's really hard to imagine a particular space where such a radical new technology doesn't have the potential for radical change. So for instance, 3D SoC, with its dense and fine-grained connectivity between logic and memory, promises significant gains for the ever-expanding broad application space of big and abundant data applications, which are currently severely limited in performance due to the memory wall, or the limited data bandwidth stemming from limited physical interconnect density bridging separate off-chip memory and on-chip compute. So many of these applications currently can spend the vast majority of their time and energy just moving data around a system. And potential applications can extend well beyond conventional computing applications. So for instance, to highlight one example, for the last few years, we have partnered in very close collaborations with Analog Devices, as well as with clinicians at Massachusetts General Hospital in Boston to develop novel three-dimensional chips that add an additional layer of CNFET sensors onto the top layer. And we're already using these chips today to enable rapid diagnostics of disease, such as respiratory infection, straight from patient breath, for instance. And though we began this work several years ago, it has obviously taken on new meaning and relevance since the latest outbreak of COVID-19, which I think just goes to highlight, again, the unexpected ways that new technologies can enable new applications in an ever-changing world. And the potential applications, of course, don't end there. There are projects we're starting to investigate, ranging from mixed signal, mixed technology, mixed node ICs, to investigating really important consequences these technologies can play in extreme radiation environments, such as space, to computing at the edge and realizing ultra-low power computing systems. I really do encourage all of you to envision ways in which 3D SoC could be expanded and exploited for your uses. And as I mentioned, we're eager and looking forward to engage with you. And with that, I'll wrap up this talk. I hope I've been able to show you that 3D SoC really does embody that saying, DARPA hard. There were and remain important challenges that had to be overcome, but the potential benefits are significant, and these benefits really do represent just the beginning. And more importantly, I hope I was able to show you that 3D SoC is not just a vision or a dream, or just some proof of concept, but rather that 3D SoC is actively transforming from a technology that was of scientific interest in academic labs into a technology that can one day hopefully be used by all of you in new and exciting ways within a US foundry. And with that, I'll conclude. Thank you for your kind attention. Thanks to DARPA and MTO again for this remarkable opportunity, and we look forward to updating you next time on the exciting things we're hard at work at right now. It's really been an honor, and thank you very much for your kind attention.
Next up, DARPA Microsystems Technology Office Program Manager, Dr. Tom Kazior.
Good afternoon. Today I would like to share with you my vision for CMOS-like heterogeneous integration. First question is, why heterogeneous integration? With all the great advances made in the performance of silicon CMOS, why not do everything in silicon? In fact, if it could be done in silicon, it will be, providing cost-effective solutions for most applications. However, silicon can't do everything. All silicon solutions cannot meet the aggressive performance requirements for emerging DoD applications. 3.5 devices, on the other hand, provide superior performance, higher switching speeds, higher frequency operation, better RF performance. An example of this is shown on the right, where we plot output power versus frequency and compare silicon technologies with 3.5 technologies. Clearly, the 3.5 technologies, gallium arsenide, indium phosphide, and gallium nitride, provide much higher power and much higher frequency operation, extending into the terahertz than the silicon technology. In addition, there's interest in being able to integrate other non-silicon technologies with silicon CMOS to provide for functional diversity. So the question becomes, how can we integrate these higher performing 3.5 devices with high density silicon CMOS? This is not a new question. There's been many approaches to try it in the past. As an example, on the left, from the DARPA DAHI program, one performer integrated indium phosphide and gallium nitride chiplets on top of silicon CMOS wafers using microbumps. Under the DARPA Cosmos program, a performer looked at the monolithic integration of 3.5 devices with silicon CMOS in a process very similar to silicon germanium by CMOS. Still, on the right, other performers looked at wafer scale integration, bonding completed CMOS wafers on top of completed 3-5 wafers, either indium phosphide or gallium nitride. While all of these techniques show promise for integrating 3-5s with silicon CMOS, they are not without their challenges and limitations. One has to keep in mind that the 3-5 devices have been optimized for performance and not for integration with other technologies or silicon CMOS. Therefore, each of these approaches have had to do modifications to the 3-5 processes and post-processing in order to make them compatible with this integration. This has had an impact on both the performance and yield of the 3-5 devices. Also, we have to keep in mind that there's not really a set of standard interfaces for 3-5 devices, which is further exacerbating the problem of being able to integrate the 3-5s with the silicon CMOS. So what I'm looking for is ideas of how we can begin to overcome these limitations. One idea that I have is, what can we learn from silicon technology? Silicon CMOS fabrication, integration, and packaging leverages the planar back-end-to-line interconnect process that's been developed for silicon CMOS. It provides multi-layers of interconnects to allow a high density of integration. It provides planar surfaces, planar interface. It's been optimized for yield, and is also, the interfaces are standard across the different silicon CMOS nodes. This has enabled all silicon monolithic, 2.5 and 3D integration solutions. An example is shown on the right, where I plot integration density versus time, and just showing the evolution and performance and density of silicon CMOS circuits from chips mounted on boards to chips mounted on interposers with microbumps to wafer scale integration or wafer bonding techniques. So the question is, can 3-5 devices look like silicon devices so that we can easily integrate them with silicon CMOS? Why would I want to do that? Here's an example on the left, is an all-silicon millimeter wave transceiver. It's a fairly dense circuit with very good performance. My vision is, suppose we replace the RF transistors with high-performance 3-5 transistors and add other levels of functionality, digital circuits, complex digital circuits, and I can build a heterogeneously integrated millimeter wave digital transceiver that provides at least a 20 times improvement in transceiver sensitivity. So my vision is that CMOS-like heterogeneous integration would be a key enabler for improving the performance and swap of next-generation DoD systems. And I'm looking for your help to solve some of these integration challenges. Thank you for your time.
This concludes our morning plenary session. Join us in the exhibit hall to view posters and demonstrations. Parallel sessions and workshops will begin at 2:15 p.m. Eastern Time.